how we just learned last time. Last time, we just learned that we can just express E as a limit. E here as a limit as this form, right? So by using this one, you can just try to estimate what the numeric number for E, right? So as I told you, you can just use some small number here to try to calculate E. So as X is smaller, then you can get a more proper E for this real number E. Okay. So by the way, you can also change the variable from X to Y by using S is equal to Y over 1 over Y. Then you can convert the whole expression as this one. So if you just use this one, you can try to use a large, very huge number for Y. Then you can get a better approximation for the E number. Okay. So at the same time, we also learn how to get the general exponential function. So in the past, we just learned exponential function. That means it is e to the power of x. But if we just talk about the general exponential function, then we will say the base is a instead of e. Okay. So I also told you that remember, convert a to the power of x to as some form with e. So remember, if you cannot remember it, please remember this one. Try to get the result by some inference by following this one. Okay. Then we also talk about the power rule, that with the support of e, then we can have the power rule to be extended to a general form. That means n here could be real number instead just n is a integer or we can just extend the idea from n to be a positive integer, then finally we can just reach a real number, not just a rational number. Okay. Then I also teach you here, you can just try to convert it by using this one. We gradually extend a to the power of x to a to the power of u. U here is a function, a differential function of x. Okay. Then we also learn the behavior about y is equal to a to the power of x. So we know no matter what a is, then that means a could be larger than 1 or a could be less than 1. Then no matter what a is, then its corresponding curve is always concave up. But different a will cause a increasing function or decreasing function. If a is larger than 1, it will be an increasing function. But if a is less than 1, then the function will be decreasing. Okay, and then we talk about how to integrate it. Then I also show you an example. Then finally, we just stop at logarithm, a general logarithmic function. Log using a as a basis, x. Actually, it is the inverse of a to the power x. Okay, and we also learn some rule for the logarithm. So I believe these 4 rules are quite similar to e to the power of x, right? Okay, so this time we just learned. So this time I will just spend some minutes we just want to talk about the derivative involving log within A as a basis, U. As usual, U is a differentiable function of x. That means blah 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 x of x. Okay? So if you want to differentiate, calculate the derivative of something related to logarithm using A as basis, remember, as I told you, if we want to calculate this one, remember, always remember, change it as ln u, ln a, right? Something like you just change the basis, right? You can just change it to this one. Then once you change it as ln function, then it will be easier for you to calculate its differentiation. Okay, so that will be, you can see here is 1 over ln a times this one. Then you know here, if you want to calculate this part, it's easier, right? That will be 1 over ln a, then u 1 over u, then du dx, right? If you just differentiate this part, you can get this one. So we can just have an example that if I ask you to differentiate log using 10 as a basis, 3x plus 1, then following this, you can see the base a here is 10, right? Then u here is 3x plus 1. So from this, the result will be 1 over ln 10 times 1 over u. U here is 3x plus 1, right? Then finally, we try to differentiate u according to x. So the result will be 3x3. So finally, the answer will be 3 over ln 10 times 3x plus 1. So this part is about how to calculate the derivative of the function with logarithm. So actually, the only tip is try to convert it as this one. So then you will have ln function. So just like I told you, if you just calculate the integral about logarithm, general logarithm, logarithmic function, remember also convert it into ln function. Okay, so I will show you a second example. For example, if I ask you to calculate this one, right? You can see we just face a general logarithmic function here again, but its base is 2. So as I told you, remember, convert this part into ln x over ln 2, then over x, then dx. So then you will just face a problem about 1 over ln 2 integral ln x as dx. Right? In such a case, you can just assign, you can just use the substitution. Did you still remember substitution? We will just use a simple variable u. We will use a simple variable u to replace a complex differentiable function of x, right? So ln(x) is a differentiable function, continuous function. It's a little bit complicated, so I try to use u to replace it. Then, okay, so let's just let u be ln x. Then just remember when we just use substitution, once you just assign u to be ln x, remember calculate du over dx immediately, that u will be 1 over x, so that we can have 1 over x dx is equal to du. So you can see here we can use it to replace this part, right? So finally we will have the form as 1 over ln 2 integral u then du. So the expression will become easier. That will become u squared over 2 plus c. And remember, we need to convert it back to something like ln 2 squared over 2, then plus c. And I hope you can just pay attention to here. ln x, sorry, ln x. ln x. ln x, yeah, square, then 2 plus c. So you need to keep this bracket because you know ln, actually this part is different from ln x squared, right? Actually this part is equal to 2 ln x, so you need to keep this one. Okay, so this is about the section 3 for chapter 7. So I also follow the old rule. I still list some questions for you. Then after you go back, please try your best to have more practices. Then as the old rule, for the first quiz, normally we will pick some questions from the list, so that we just want to make sure if you really do some practice by yourself. Okay, but if you can practice more, it's even more welcome. Okay, so this is section 3. So any questions about this part? And supposedly we need to move to section 4. However, because section 4 is talk about the differential equation, so if supposedly when you study here for your second year, you need to take engineering mathematics. Then one of 2 engineering mathematics classes, you will get involved in differential equations. So I will not talk about this part, but I think this part is also still very important. But if you have time, please just spend some time to review the concept about the differential equation. And especially there is also a very important concept about the exponential change. You know, exponential change is also very, how to say, it's a little bit scary. Maybe I also share a short story with my students that it's an old story that you know, one general, he just helped the king win some war. In some war he just win, and then the king tried to give some reward to the general. So he just give the general 2 choices. The first one is, okay, I give you 1 piece of rice, and for the following day I give double. So that means for the following day you will have 2 pieces of rice. Then the next day you will get 4, then 8, right? The second condition is every day I give you maybe like 10 kilogram of rice constantly. So finally, the general just choose he just prefer to get a constant offer. That means I can get 10 kilograms every day. I mean about rice, but actually it's a best selection, because if you get 1, then the following day is a double of the previous day, then you can get more. Okay, so it's very interesting for session 4. If you have time, you can just spend some time to study. 我很快讲一下，其实是我们就不讲了哈。其实是有2个重点，一个是 exponential change， 一个是微分方程式。那微分方程式因为在大2的时候就会整门课都在讲微分方程式，所以我们就让微分方程式那边在比较专注在解微分方程式，因为微分方程式它有很多策略、很多方法去解微分方程式，所以在微积分呢，我们只谈到基本的微分跟基本的概念。那微分方程式就是解一个方程式里面它有关于它的解所以这个我们就不在这边讲。那第2个他有提到公数的，我不知道是上学还是下学期有点忘了。It's a part 1 or part 2 for the engineering mathematics. I mean the differential equation. Did you remember? Part 1, right? The part 2 is about linear algebra. Okay. Part 2, okay. 应该是上学期吧那我要讲的第2个观念是这个 exponential change 这个是非常有趣的。其实特别是在疫情期间，这个常常有人在讨论这个问题，就是你知道，或者最近的这种流感嘛感冒这种是种具有传染力，它事实上是跟 exponential change 是有关系的。那我刚很快讲一个故事，就是说有一个国王嘛，他的将军帮他赢了战争，那就论功行赏那他有2个选项来奖赏这个国王来奖赏这个将军嘛，他就说有2种选择，一种是第一天我给你1粒米，第2天给你前1天的2倍，就是变2粒米了，对不对？第3天4粒米，然后再8粒米，对不对？然后另外一个选择是我给你每天10公斤的米。那这个显然这个将军是没有学过微积分他没有想到他就选了每天10公斤所以他显然是不过这个等一下我们来讲他的 part 2 好了。显然他没有学过微积分，因为这个 exponential change 才恐怖一开始可能1粒米、2粒米、4粒米、8粒米、8在每次就是前面的 double 嘛16就是32、64、8这样上去，到后面的时候那个指数型的成长是非常恐怖的。但是他取的如果是 constant， 每天都10公斤10公斤，10天就是100公斤嘛它就是一个 constant， 所以它永远就是停在那里。可是也许在一开始它是进步很慢的，但是到最后它会突然就变得很快这在计算机科学里面有提到这个问题，这个我们称之为 non-polynomial 的时间，它时间非常快，很巨量如果你要算的是什么 n 平方 n 的3次方这种 order 都算是小事。我们今天也会讲今天应该会讲到一部分这一块事实上都像我们称之为所谓多项式时间，就是几次方 n 的平方 n 的3次方 n 的4次方哪怕 n 的100次方，其实它都比2的 n 次方还来得小很多所以国王给这个将军显然是做一个错误的选择他只是拿了一个n 乘以 x 这样的一个选择，所以 n 乘以一个常数100，然后10公斤或者是10或者100公斤这样子。但事实上没料到后面是非常的快不过我事后 想想这个将军选的没错，对不对？如果前1-2天他给1粒米，第2天是2粒米，他恐怕在前10天就饿死了，有没有道理？对不对？前10天他就饿死了，哦，所以看起来这将军选的也不是错了哈。但如果你长期来看哈，他如果要帮他子孙累积够多的财富的话，其实应该选择1，对不对？那个 exploration 才会很恐怖。那这件事也反映到疫情，就是这个传染力哦。一开始你可能觉得很少啊，一个人感染没问题，那再2个就变4个了，4个就变8个哦，就是后面就很恐怖，就没办法收拾哦。所以这 exponential change 也是非常有趣的一个议题哈。所以这个虽然没有时间讲，那它里面讲到这个辐射的这个所谓的半衰期，对不对？大家如果学过物理或者是化学，这个辐射的半衰期，它其实跟 exponential 有关系。所以这个就请大家回去的时候再稍微可以看一下这个有趣的议题，针对 exponential。那如果没有问题的话，其实我们就直接会跳到7支。OK， 我们就会跳到等一下哈。OK， 好。好。Okay, so then we will move to section 5. So that means we will not include section 4 as our quiz, as our scope of quiz 1. Section 5 is talking about indeterminate form and the Hospital's rule. So let me just show you the theorem about the Hospital's rule. So what is the Hospital's rule? Let me just show you that in the past, especially when we just study the concept about limit, we try to get the limit as x is approaching a, f of x over g of x, right? So at that time, we just simply put a into a function and also g's function. So we try to evaluate f of a, then g of a, right? So in the past, if we just encounter one situation that if f of a is equal to 0 and g of a is equal to 0, then at that time, normally we just do this way. We try to factorize it into x minus a here, then blah, 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 right? Because if f of a is equal to 0, that means if f of x can be factorized, then suppose we can just get x minus a factor. So similar to g of x, if g of a is equal to 0, then we can try to factorize g of x with a factor of x minus a. So that we can just cancel it and try to continuously use a to replace x. Then we can continuously get the final result. So this is the way we just proceed when we just encounter this situation. But in this case, we need to make sure if f of a and g of a can be factorized with this factor x minus a. But if you just encounter the function cannot be factorized, how should we do? So we just list the theorem here. Suppose that f of a and g of a is equal to 0, and f of x, g of x are differentiable on an open interval I containing A, and we also assume g prime x cannot be 0 on the same I if s is not equal to A. Then this part is the most important part. If you calculate this one, you just suddenly find if f of A is 0 and if g of A is equal to 0. You can do this way. Then try to differentiate f of x and g of x. Then you can just find the result will be the same. So that means if in the beginning f of A is 0, g of A is 0 also, then try to differentiate f prime to f of x, then you can get f prime of x. And also try to differentiate g of x, then you can get g prime x. You can just try this way. And then again, you just repeat the process again. Use A to replace x here, and to see if f prime A is 0, and here is also 0, g prime x of A is also 0. Then you can try to continue this process to this one, double prime x over g prime x. So you can just continue the process until one of these two functions is not 0 anymore. Okay, then you can get the result. Can you understand the process? So I will show you an example that, okay, let me just show you an example that, for example, if I ask you to calculate a limit s is equal to 0, square root of 1 what is that? 1 minus x, or 1 plus x, okay, minus 1 minus x over 2 and over x squared. So you can see here is f of x, here is denominator is f of x squared, numerator and denominator, right? Both of them, when you just use 0 to replace x, you can find here 0 minus 0. So anyway, here totally it will become 0. So at the same time, x squared 0. So you will suddenly find it will follow 0 over 0, right? 0 over 0. So that you can follow this. Try to differentiate f of x. Try to differentiate g of x. Then you can get f prime x and also g prime x. So you can get, so we can try to get limit because 1 over 0 over 0, right? So we can just differentiate both functions so that we can have 1/2 times 1 plus x to the power of negative 1/2. Then because this is minus 1, so when we differentiate it, it will become 0. Then this is 1/2 x. When we differentiate this part, it will become negative 1/2. Then for x squared part, when we differentiate it, we can get 2x, right? So then you can try to use 0 to replace s again. If I use 0 here, you can see it will become 0 again, and also 0 again. So we can just do it again. So we just find, okay, it will be 0 over 0 again, right? Right? When you just use 0, here it will be 1 half minus 1 half 0. 2x 2 0 over 0. So it's still 0 over 0. So we can continue to differentiate it. So we can get limit s still is equal to 0. Then negative 1/4 1 plus x minus to the power 3 halves. Then this is 2. Okay. Right now you can see someone. One of these two will be non-zero. Even here is also non-zero, right? So then you can just get the result by using negative 1/4 1 plus 0 to the power of negative 3 halves and over 2. So the result is this one. Okay. So the rule is simple. You just continuously differentiate both parts, and once someone will not be 0, then this is the final result. Okay, let me show you another example. So here, so when x is equal to 0, 1 minus cosine x over x plus x squared. So you can see in the past, if you just encounter a polynomial function, you can just factorize it. So you can factorize it, it's fine. But this is not a polynomial function, so you cannot factorize it as having a x factor. So in this case, you cannot do it like this way, right? You cannot do it like this way. This example also, right? It's not easy for you to factorize it as this one. So in this case, we still can apply the Hospital's rule. That you can see if I use 0 to replace this one, then you can get it will be 0. Then 0, 0, so it is 0. So you can see, this is 0 over 0. So we can continue to calculate limit x is equal to 0. It will be sine x over 1 plus 2x. Then you can just use 0 to replace this one, use 0 to replace one. So you can see here is still 0. But here it will become 1. So please notice that this is 1. This is non-zero. So you need to stop here. Okay? Please do not continuously differentiate both sides. That will cause a wrong result. So suppose you will stop here. So the answer will be 0. Please just stop here. If you continue to calculate this one, okay, cosine x then 2, then you will say this is 1/2, then this is wrong, this is correct. What I show you is you need to stop here. Don't continuously differentiate both sides, then finally you will get a wrong result. Okay, so this is wrong. Okay, so why we say this case is a indeterminate form? Because why we say this in indeterminate form? Because why we say it? Because the result could be 3 possibilities. The first one is I can give you a concrete number, like this one. Finally, we can get a concrete number. The second one is it possibly becomes 0. The third one is infinity. I believe you still remember infinity is a meaningless number. So actually, 3 possibilities. One of the 3 possibilities will happen. So that's why we call it indeterminate form. That means I cannot make sure the result will be is a meaningful or a meaningless number. So this is we call it indeterminate. So normally for the indeterminate form can be like we just encountered 0/0, or infinity over infinity, or infinity times 0, or infinity minus infinity. So these four forms, all of them are indeterminate. That means I cannot make sure what the final result is. Instead that you just try and follow the rule. Okay? And at the same time, the indeterminate form, when you just calculate, you just face the problem, x is approaching a here, can be s is approaching a plus. This is about the right limit, right? This is about the right limit, because x is approaching a plus. That means x is approaching a little bit more a, right? So x could be s is approaching a plus, or s is approaching a minus, and a could be finite or infinite. That means like this one, or positive infinity or negative infinity. Both of them is fine for the L'Hopital's rule. Okay? Okay, let me just show you that one example. For example, if I ask you to calculate limit s is approaching 1/2 pi secant x over 1 plus tangent x, right? So when you calculate this one, did you remember we just simply use this as an input for x, and for this one tangent x, right? But did you still remember this is about two-sided limit, right? This is for two-sided. If you forgot, please just go back to chapter 2. This is for two-sided. So two-sided means that there are two parts. We will talk about the limit. S is approaching 1/2 pi plus, and limit s is approaching 1 half pi minus, then face the same expression that second x over 1 plus tangent x. This is a second x 1 plus tangent x, right? So we try to calculate its right hand limit and try to calculate its left hand limits. If we can have two-sided limit, we should measure its two one-sided limits. Then if two one-sided limits are the same, then we can conclude its two-sided limits exist. 之前我们有学过这个，对不对？如果我要确保它的双边极限，这是双边极限，对不对？如果忘了回去看一下哈，就是两边的极限，它其实上是可以区隔成两种，一种是 x 趋近于 a 的多一点点的，一种是 a 趋近于少一点点的。所以这两个极限如果都存在且相等呢，我们就说它的双边极限存在。这个我想是第2章的时候我们有讲过哦。好，如果要算这个题目呢，我们其实应该去算这两个双边极限，看它确保有没有存在且相等哦。Okay, so that means we can just focus on this part. So we are trying to get limit s is approaching 1 half pi plus second x 1 plus tangent x. So when we just use 1 half pi plus to replace x here, then we can get positive infinity. So similarly, if we just use this to replace tangent x here, then we also can get positive infinity. So you can see we just encounter infinity over infinity, right? In the past, here we just encounter 0 over 0. So if we just encounter infinity over infinity, we still can apply the Hospital's rule to solve this problem. So we can try to differentiate second x so that we can get, after we just differentiate, we can get second x tangent x. When we differentiate this part, we can get second square x, so that we can just cancel one time. Then we can get, here is sine x over cosine x. Here will be simply 1 over cosine x, right? So that we can just cancel these two parts. Then finally, the whole result will become sine x. So that means we are talking about limit s is between 1 half pi plus sine x, and the result is 1. Okay, let me show you. 这个我们在算两边极限，我们把它拆开来看，先看单边就好了单这一边呢，这是 x 趋正的，就是右极限这一块呢，它是 sin x 除以second x 除以1加 tan x， 所以你就试把带进去，还是得到无穷大分之无穷大。所以这件事情告诉我们什么？罗必达法则也同等适用在无穷大除以无穷大这种案例里面，也同时适用于它在做单边极限计算的时候也可以用。不仅仅它只在双边极，它也可以在单边极限，或者是当 x 趋近正无穷大或负无穷大都可以用。只要你遇到0分之0、无穷大分之无穷大、无穷大减无穷大跟0乘无穷大这种案例的话，你都很合适用这个。那唯一你要做的是什么？你要把它变成一个有理，这就是 rational expression， 有上下，然后可以重复不断的一直被微分直到什么时候呢？表示这微分下变成 second x 这 second x， 所以这时候变成 sin x sin cos 除以1除以 sin x， 所以一除下来剩下 sin x 存在，所以这个时候就可以算了，对不对？好，再减OK. So similarly, you can just apply the same rule for limit. This is part 1. For part 2, you also can calculate x is approaching 1 half pi minus second x 1 tangent plus tangent x. So following the same process, you can see finally is 0, 1. So eventually, we can get these two results. So we can conclude limit s is approaching 1 half pi second x over 1 plus tangent x is 0, is 1, is 1. Okay, so we can just stop here. And then we can conclude the final result is 1. Because we already get the two one-sided limit. 我们拿到了两个单边极限 two one-sided limit. And also, these two one-sided limits are the same. Both of them are 1. So we can conclude is double-sided limit exists and the value is 1. Okay, so it's almost time to break. So let's just stop here and then take 10 minutes break and then come back to the classroom. Okay, so let's continue. So sometimes we also encounter another indeterminate power. So what is indeterminate power? That is about 1 to the power of infinity, or 0 to the 0, and also infinity to the power of 0. So actually, these three forms are not acceptable because you can see power here is infinity. Infinity is meaningless, right? 0 to the power of 0. So we just learned from the past that actually 0 cannot be the when the base is 0. The 0 could not be the power. And also we cannot have infinity as the base. But these three forms, actually, when we just try to convert it as a limit form, we can try to find its limit value. So how can we do that? Actually, I also show you before that actually this one is just like a one number. It is very close to 0 times someone close to 1, and we have infinite number of this number times together. Then, as I told you, the answer is E. Did you remember that? Did you remember that? Okay, so let me just show you the general concept. If we can calculate limit s is from a ln f of x, then the result is L. Then we can get limit s is from a f of x as limit s is approaching a e ln f of x. Right? Did you remember? We can have this converted into e to the power of ln f of x. Then we can get the answer will be e to the power of L. Right? If we already have this, then when we take this one, we can simply get limit. So this is a general concept, but I will show you some example. Then you can know how to get the concept. That, for example, if I want to calculate, please just show me that limit s is 0.0 plus 1 plus x 1 over x is equal to e. So you can see here, this expression just exactly depicts this result. You can see limit s is approaching 0 plus. 0 plus means here is 0 plus, right? A little bit more than 0. So then when we just have 1 plus x, this number will be a little bit more. So that means a little bit more, somewhat a little bit more. So that means it's almost equal to 1. Then times together infinitely, right? Then the result is e. So infinite is here, 1 over some value. This value is very small. It's very, very close to 0. So this is an infinite. So here you can see, here is almost equivalent to here. Then here is here, right? So then I will show you how can we just prove this one. So the first thing is, I just let f of s is equal to 1 plus x to the power 1 over x. So if we want to let the power down to the ground, down to be the coefficient, we can do one way is f of s, we try to calculate its Ln value. Once we put Ln here, we can make the power to be put to the ground, so that we can get, it will become 1 over x Ln 1 plus x, right? We can let this one be moved to the ground. Then Ln 1 plus x here. So with this, we also can continue to calculate limit s is 0.0 plus then Ln f of x. So we can get, this will be limit s is approaching 0 plus then Ln 1 plus x over x, right? I just simply use this one. Okay, so when we calculate this one, you can see when I use 0 plus here, so what is the value? That will be Ln 1 plus 0 plus. So the value will be 0. Then if x is 0.0 plus, here also 0, right? So we just get 0 over 0 form, so that we can just apply the Hospital's rule. So we can get limit s is approaching 0 plus, and try to differentiate both functions, right? So it will be 1 over 1 plus x and also 1. So this will be 1. Right? Finally, this limit will be 1. So according to the, if you want to get, so that you can get, if you want to get the limit s is approaching 0 plus f of x, f of s is here, right? F of s is here, f of s is here, f of s is here. So that means if you want to get limit s is 0 plus f of s, then that will be limit s is 0 plus, then e to the power of ln f of s. Then you already have this limit. So this limit is 1, so it will be e to the power of 1. So finally, the answer will be e. Let me just show again. You already have limit x is equal to 0 plus ln f of s. So the answer is 1. So right now, go back to the original request. They just ask you to calculate limit x is equal to 0 plus f of s. So that would be equivalent to get the limit, which is where x is equal to 0 plus e to the power ln f of s. So we already have this part. This is 1, so far. Okay, so you can see two processes. Originally, you want to get the limit s is approaching a f of s, but you can try to calculate limit. Originally, you want to get this one, right? Yellow part. But since it's about a phone with some power, so we just try to make the power part to the ground. So we just check its ln value. But eventually, you still want to get limit s is a f of s. So this is process 1, but you need to get it back. So this is still your target, your goal. You want to get this one. So finally, you need to use e to make it back. 这边有一个很重要的技巧写在这里哈，这个是这里面的最精髓的部分哈。这个有时候你要算一个极限的时候呢，我等一下再举个例子啊，不用担心。有时候你要算一个极限的时候，是 limit x 趋近 blah 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 f of s 的时候，这 f of s 假如它有一个指数的形态在那里的时候，有一件事情很适合你去做的，就是先想办法去取它的 ln。因为我们知道取了 ln 之后，取了一个那个自然对数的时候呢，它会把让的次数啊幂次掉到地上来，对不对？比较好算，对不对？但是题目问的还是要问你的 limit x 趋近 a 的 f of s 啊，所以你要想办法用一把它取回来。哦，这就是这个的精神，整个精神在这里。所以我们给你的第一个例子，这个之前我们也证明过了，对不对？我们当初证明不是这样证的，但是一旦是这样子的话，我令 f of s 是这个的话，你就可以先取，因为 ln x 呢可以让这个幂次掉下来，哦，所以你看这个幂次就从半空中掉到地上来了，那去乘 ln x， 然后先去算它的极限，哦，所以一步一步来，接下来是算这个的极限，算出来它是1。千万不要停在这里哈，这不是最后的答案。为什么？你这时候算出来只是 limit x 趋近0 plus 的 ln of x， 不要忘了，我们真正要算的是 limit x 趋近0的 plus 的 f of x。所以从这里，从这里要变回到真正它的要求的时候，不要忘了是要取这个1，把它取回来。OK。So let me just give you another example. If I ask you to calculate positive infinity, to the power of 0. What is that? What is that? So if you want to solve this problem, the first thing for you is we just let f of s is equal to x to the power 1 over x. Why I assign f of s to be x to the power 1 over x? Because when x is approaching infinity, the base will be infinity, but the power will be 1 over infinity, so it will become 0. So if I set f of s to be s is s to the power of x, so when I calculate limit s is approaching infinity f of s, that means limit s is approaching infinity x to the power s 1 over s, that you can see here is infinity, then the power part is 0. So you can see exactly the same, right? Exactly the same as this one, right? So our setting here is correct. So for the next step, as I told you, that once we want to make the power come to the ground, what we should do, we try to have an n here, so that we can make ln x to the power 1 over x, then it will be ln x over x, right? Because we can move here to the ground, then we can have ln x over x here. Then we continue to calculate its limit. Then ln f of x. So that means we are trying to get limit x is approaching infinity ln x over x. So again, you can see when x is approaching infinity, then this part is still also infinity. Then this part is also infinity. So we just encounter infinity over infinity. It's a typical indeterminate form. So we can just, based on this, we can try to apply the Hospital rule. Then we just differentiate both functions. So we can get this 1 over x, because we differentiate it, right? We differentiate, we can get this one. We differentiate, we can get 1, right? So the answer will be 0. So here, please do not stop here, because at this moment you just get limit s is approaching infinity at the end of x. Our main goal is we want to get limit s is approaching positive infinity f of x. This is our final goal. So how can we just get back? We need to have e here, then ln f of s, so that you can see here is 1. So the answer will be e to the power of 0. So 0. So finally the answer is 1. So that means finally infinity to the power of 0 is 1. Did you remember every number, we use any number as a base? When we set its power is 0, everything is 1, right? So right now we also even furthermore improve to prove that infinity to the power of 0 is also 1. So you can see we just apply the rule to take ln value first. Try to move the power. come to the ground, then calculate its limit. So you can see this is the first step. This is the first step. The second step is try to get its Ln value. The third step is try to get its limit. The first step is just go back to the original request. This is 4. So there are 4 processes to get such kind of indeterminate power. So you can go back to your home to try to find 0 to the power of 0. You can just set a function. So right now I already proved this one, right? And also prove this one. How can you just prove this one? You can set function as x to the power of x, right? Then take limit s is upon 0. So you need to design, you need to set the function to fulfill the request here, 0 to 0. So you can see, if I want to get infinity to 0, I just design the function here, that x to the power of 1 over x. So this first step is very important. 就是你要去算这种所谓的不定型的这种幂次的时候，所谓不定型的幂次就是这3种嘛，就是你不确定这个答案是多少，因为这个以前啊，其实就以前的学习里面，我们事实上是不允许有这种0的幂次0这种计算的，但是因为这个值可以透过极限来逼近它的值是多少，所以我们就是设计一个函数，通常都是跟这个幂次有关系的函数，对不对？比方以这个例子来讲，我想要得到1的无穷多次，那我就设计这个函数是1加上 x 的1除以 x 次方。当 x 趋近于0的时候，你就会形塑出这个样态，对不对？如果我想要算无穷大的0次方，那我去设计一个函数叫 f of x 等于 s 的1除以 x 次方，让 s 趋近于无穷大的时候，它就会得到无穷大分之0。那如果现在我要设计一个函数去符合0分之0的0次方呢，我是不是要设计成 x 的 x 次方，让 s 趋近于0，那你就可以试图去用极限的方式去算出这个不确定型的 power。Okay, so this part is about session 5. Okay, this is session 5. Then we will just temporarily move to session 8. Then after we finish session 8, then we just come back to session 6 and session 7. Because session 6 and session 7, we need to take a lot of time to do that. So let's just temporarily move to session 8. So, okay. So we just go to session 8 first, then go back to session 6 and 7. So session 8 is talk about the relative rates of growth. So we just define that what is rates of growth as x is approaching positive infinity. So our define is just like that. If we say f of s grows faster than g of s as s is approaching infinity, if limit s is approaching positive infinity, f of s over g of s is positive infinity, or limit s is approaching 0. Sorry. Then we just upside down g of s, f of s, it should be 0. So when we just want to compare the growth rate for two functions, we can just simply take its ratio first, then calculate its limit as s is a very positive limit, then see if the final result is infinity. So it's easy to understand the concept. If s is very large, then finally the ratio will become infinite. So that means f of s is faster than g of s. Or with the upside down. So this is still infinity. We just upside down. We just move f of s from here to here, g of s here to here. So if we just upside down, then you can see the result should be 0. So if we just meet this requirement or this requirement, then we will say f of s is growing faster than g of x. So then we say f of s and g of s just grow at the same rate. Then if limit s is positive infinity, f of s over g of s is equal to L, then L here is a finite and positive. If we say they have the same rate, then we can say we can find f of s over g of s when we take its limit value as s is approaching infinity, the number should be L. Okay? So let me show you that, for example, we say e to the power s grows faster than s squared as s is approaching positive infinity. So if we want to prove it, we just try to get the ratio e to the power x divided by x squared, then take its limit as s is approaching positive infinity. So we can see if you want to calculate this one, then just use infinity to replace s. So we can get infinity over infinity. So we can get infinity over infinity, right? So it just fit the requirement for the Hospital rule. So that we can just continue to differentiate both parts. Then we can get e to the power x for x squared, we can get 2x. So again, when I use infinity to replace x, we can get infinity. So we just get infinity over infinity again, right? Continuously calculate its derivative. Then we can get e to the power of s. Then this is 2. So finally, we can get the answer is infinity, right? Because someone is not 0, someone is not infinity. So we can just stop here. So to the end, the result is infinity. So that means this part is faster than this part, right? Of course, you can just upside down it, and then you can get the result, it will be 0. Okay, so you can just also image that all polynomial function or or other power could be slower than e to the power x. So you can find actually you can try to calculate ln x is slower than x, then x will be slower than x squared, then blah 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 to Sn, then blah 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 s less than e to the power x. You can just simply pick any two of them to get its value, its linear value as s is a very constant. 这个检测呢，就是让你知道，就是说函数跟函数之间啊，我们都知道这不管是 x 的二次方或 e 的 x 方，随着 x 越来越大，或者 ln(x), 它们都是往无穷大跑的。可是大家都在往终点线无穷大跑的过程当中，有人快，有人慢。其中最慢的是 ln 函数，但是你不要小看它哈，龟兔赛跑。乌龟走得再慢，它其实还是往终点在走，对不对？它们的共同的终点就是无穷大，只不过乌龟跑得比兔子慢，可能跑得比这些狼啊这些慢，但大家都是往前跑的，但是跑得最快这个是 e 的 x 次方，它成长的最快，所以刚刚不是跟你讲了，这个将军做了一个错误的选择。将军选择了 x， 他忘了 exponential 是更强大 ，e 的 x 方跑得更快，但是他短视近利，他以为 x 就已经够好了，其实后面这边 e 的 x 还更厉害。这里面哪怕你的 x 是1万次方、1兆次方，你都比 e 的 x 次方长远来看你是比较慢的。所以你有没有注意到，其实我们关切的是什么？在 x 在趋近无穷大的时候，我们不会只短视在 x， 只在1万、1兆，我们事实上是关注在它在很大很大的时候，事实上 e 的 x 次方这件事情是成长的非常的巨大的所以我们会利用这个方式来量测。那在这个量测里面呢，事实上你可以，你看是 f 去除 g of s 也行。G of s 去 f of s 也行，不管怎么样，如果它出现结果是无穷大或者是0的话，你就可以判断两个是有以这个例子来说，分子的部分是比较快的，分母是比较慢的。如果反过来，这个相除之后的取极限值是0的话呢，分子是比较慢的，而分子是比较快的。那有一种情况是大家差不多两个旗鼓相当，那个例子是在如果两个相比取 s 趋近无穷大的时候，它得到一个常数的话，那就会差不多。比方说2的 s 的平方跟5的 s 平方，这两个谁跑比较快？其实这两个到最后是旗鼓相当的那个常数的部分没有什么只是一个常数的关系，但是当 s 无穷大的时候，事实上两个是差不多的Okay, so I will show you another example that limit we will show that ln(x) grows slower than x as s is approaching positive infinity. So again, if I ask you to evaluate the growth, then you can try to just put the ratio for ln(s) and x, and try to calculate its limit. Then you can see here is positive infinity, this is positive infinity, so we encounter positive infinity over positive infinity. So we can continue to calculate limit x is approaching positive infinity. This part is 1 over x. This is 1. So finally, we can get limit s is approaching positive infinity 1 over x. Then value is 0. So you can just see, if we just put this ratio and calculate its limit as s is approaching positive and the final result is 0, we can say that ln x is slower than x, right? And then I will show you some other example that we will please just show a to the power s grows faster than b to the power s, where a is larger than b and both of them are positive. So what should we do? What should we do if I ask you to prove this one? Okay, if we want to show this one, we just simply use a to the power s divided by b to the power x. Then take limit s is approaching positive infinity, right? If you want to compare these two functions, just use f of x divided by g of x, then take its limit. Let's just see what's the result. If the result is positive infinity, then we will conclude this one is faster. But if the result is 0, this part is slower. Okay? So easy, right? Then you can continue to get this one. This one is the limit s is positive infinity a over b to the power x. Since a is larger than b, so this number should be larger than 1, right? Because a is larger than b. So when we use a, when we calculate a divided by b, the number should be larger than 1. If the base is larger than 1, when you calculate this as use it as a base to the power of x, as x is approaching positive infinity, the result is positive infinity. So we can conclude. So we can conclude this one: a to the power of x grows faster than b to the power of x. Then okay, let's just. So this is a general exponential function, right? So how about general logarithmic function x and this one? Actually, the result is very interesting. Goes at the same rate as this one. It's very interesting. You can see a to the power x grows faster than b to the power x. Both of them are general logarithmic functions, but general exponential functions. But these two ones are general logarithmic functions, but actually they grow at the same rate. So how can we prove it? So again, we just try to use logarithmic function using a as a base, x over log using b as a basis, base, x, and then we try to calculate its limit, right? So see what will happen. What will happen? So just remember, when we calculate this one, I just told you that the tip is try to convert it as ln x over ln A. For log using B as base, X, it will be ln X over ln B, right? Do you remember I just told you this is a very important tip. You need to convert it as this one. You need to convert it as this one. That's might change your base. Then we can just get the result is cancel. Then this is constant. ln A is constant. ln B also constant. So the final result is ln B over ln A. So see here it's a constant. So if it's a constant, did you remember our definition just showed that if this ratio is a constant, positive, and finite, then we will say these two functions just grow at the same rate. So that's why we conclude that these two functions just grows at the same rate. Okay? And as for section 8, if you just check out the textbook, you can find this section also include small o and big O. So we will bypass this part because small o and big O is used for evaluate the complexity of algorithm. So when you just study data structure or you study algorithm, if you want to evaluate how complex the algorithm is, we will use small o and big O to evaluate. But this part is just out of our scope, so I just also skip this part. So maybe we just stop here for the section 8. So also this some question for your reference. 这一章节里面它还有课本你去看一下。也许我列的题目里面可能也不小心有列到 big O 跟 small o， 但是我还是鼓励大家去看了，虽然没有讲，还是去看，但考试不会考哈。但是呢 big O 跟 small o 就是有这个概念，就是让你知道它的 order 的概念哈。我举个就简单的例子来讲了。这个7×8没有错。7多少？这边应该是7×8啊，对吧？我先跳到7×8，7×5完以后，我们先跳7×8，然后7×7、7×6，我晚一今天没办法讲了哈，明天下礼拜以后再讲啊。我说那题号呢？题号？我说那没有，我是说那章节的我的2是7×，你写错了。7×8，没关系，不然等一下你来找我好了，好吧？这是7×2的题目。那我很快讲一下，就是大家回去还是可以看一下那个小 O 跟大 O 的概念哈。它是在表达一件什么事情呢？比方说好了，我举一个例子 ，s 平方加 sin x 跟 s 平方来比，其实这两个是差不多的。为什么？你想一想 ，sin x 它只会在0、1里面震荡，对不对？可是你加了 s 平方，所以 s 平方已经 dominate 了整个函数的发展。当 s 很大很大的时候，其实那 sin s 起不了什么作用的，所以它跟 s 平方事实上是差不多的。所以这时候我们就会有你这个 big O， 你的 order 大概就是在 s 平方这个。同样的，如果 sin x 加上1加上0加上 0.5， sin x 呢 dominate 了就好像你如果要去买一个 LV 的包包，对不对？那大概你这个包很贵，所以它比方说里面这个譬喻不是很好。我的意思就是说，当你在买一个 iPhone 的手机好了，那买了一个 iPhone 手机可能好几万块，对不对？那你到时候买一个 cover， 买它的什么？它的这个cover 是什么？就是你们手机不是都会有一个保护套吗？它可能只有几百块，甚至是几千块，甚至是1万块，你都觉得它没有很贵。为什么？因为像这样你的 iPhone 手机 是5万块、4万块的价值，那你去把它包个膜，可能2000块了，那时候它就不算什么。可是包个膜要1、2000块的话，相较于你等一下去吃个便当，吃一餐可能50块、80块，这包膜就好像还挺贵的，知道我的意思吗？所以我们在做计算机演算法的讨论的时候就会这样，就是你很多看事情的时候，你去看那个大的，会大面累你整个计算量的那个才是你最关注的，那其他那个 piece of cake 对你来讲它是 piece of cake， 我们就可以把它bypass掉，对不对？相较于1亿的时候呢，你的5万块已经不算什么了，可是5万块相较于你的1000块的时候，5万块就好像是很重要，对不对？但是1000块又相较于你的便当80块、100块的时候，那是这个时候这个便当的费用又不算什么，这样了解我意思吗？所以后面有这个章节来讨论这一部分，但那个不是我们这边会用的，所以我就没有在这边提，但是是在跟比这个有关系的时间差不多，因为接下来可以预告下面的2个章节讲起来都很痛苦，你们应该也会，所以我想说我们就先把简单的部分先讲完，然后7至6、7至7下礼拜一来我们再讲。OK， 好，我们今天就上到这里。
今年我有讲。